Welcome to Lecture 3G. We're going to keep on our discussions of equilibrium. In this particular section, we are going to talk about equilibrium concentrations. So for equilibrium concentrations, in the previous section we talked about if we were given the equilibrium concentrations, we could calculate the equilibrium constant as long as we have the balanced reaction. Well, now we're going to go in a little bit different direction. Now, if we know the equilibrium constant and the initial concentrations of the reactants, we are going to be able to calculate the equilibrium concentrations for the reaction at equilibrium. And we use something that is called an ice box. And here we go, we got some ice baby. Oh, look at that, it's a little ice baby. Oh, that's just disturbing. So what is ice here? So ice, I, initial concentrations, C, are changing concentrations, and E are equilibrium concentrations. So this idea of an ice box is going to set up our calculation for our initial concentrations that were given, the changing concentrations, which is going to be an unknown, and the equilibrium concentrations, which is the sum of the I and the C. So let's take a look at an example here. So I have a very basic reaction here, A turning into B. It has an equilibrium constant of 24. We know that the initial concentration of A is 0.85 molar. We want to know what is the value of A and B at equilibrium. What are the concentrations of A and B at equilibrium? So let's set up our ice box. So this is an ice box right here. We have our initial, our change, and our equilibrium. So we know our initial concentration of A is 0.85. Our initial concentration of B is 0 because we weren't told the concentration of B. It's the product. That's usually 0. Not always. It is certainly possible to have an initial starting concentration of a product. We may see some examples of that. Now the change. How much did the concentrations of A and B change? Well, we don't know that. If we knew that, we wouldn't have to do the ice box. So we're going to set that as X. And what we're going to set as X is the amount of A that is lost. So we're going to lose X amount of A. And notice that because my reaction has a 1-to-1, for every 1 A lost, I gain a B in this reaction. So for every X amount of A lost, I'm going to gain X amount of B. So I lose minus X of A, I gain X of B. And so at equilibrium, this is just the sum of these two values. If you want, I can draw a little line right there and a little line right there. So 0.85 minus X is equal to 0.85 minus X, and 0 plus X is equal to X. So we don't know our equilibrium concentrations yet, but we do have them set up as a single unknown variable. And if I have an equation with a single unknown variable, I can solve that equation. So here's our equilibrium constant expression. At equilibrium, it's going to be equal to the concentration of B over the concentration of A. They have no exponents because their balancing coefficients are both 1. And so we know that that equilibrium constant is equal to 24. So we plug in the values we know. We know the concentration of B at equilibrium is X. That comes from right here. And the equilibrium concentration of A at equilibrium is 0.85 minus X. So that comes from right there. And we know that that has to equal 24. So we do a little bit of algebra here, and what we find is our X value is equal to 0.816. We see that X is also equal to the concentration of B, so now I know my B concentration. And we know that my A concentration is 0.85 minus X, so that's going to be 0.85 minus 0.816, and we get a concentration of A at equilibrium of 0.034. So that's how you do an ice box, quick and dirty. That was a very basic reaction. We certainly have some that are more complex, and here's one of those examples. So here we have H2 plus F2 going to 2HF, very similar to our iodine reaction, but slightly different elements there, we also have a slightly different equilibrium constant. So we have initial concentrations of H and F of 1 and 2 respectively. That means that my H2 is 1, my F2 is 2. We want to know what the equilibrium concentrations are for each of those components. So we set up our icebox, and I apologize, my little spreadsheet here did not include the extra digits for these for some reason. But we have our initial concentration of H2 at 1, initial concentration of F2 at 2, and my concentration of HF at the start is 0. Now, how much am I going to make, or how much is it going to change? Well, I'm going to lose X amount of H2. I'm also going to lose X amount of F2. They're both reactants. You're always going to lose reactants and gain products. Okay, it's just a good convention to go with for your ice boxes. Now, the HFC here is 2X. Okay, and the reason for that is because for every one H2 and one F2, I gain 2 HF. So if I lose X amount of H2 and X amount of F2, I gain 2 of HF. Okay, it's not because 1 and 1 are equal to 2, it's because the stoichiometric coefficient here of the HF is 2. That's where this 2 comes from. So this 2 here and this 2 here are linked. Okay, so now we know what we started with, we know how much things to change, and now we can calculate our equilibrium concentrations. That's going to be 1 minus X for our H2, 2 minus X for my F2, and just 2X for my HF. So now we know our equilibrium concentrations. We can plug those into the equilibrium constant expression. We see that our Kc is 115 given in the problem. And again, that's something that's either given to you or something you could look up if you were in the lab. We know that it's going to be equal to concentration of HF squared because of the 2 coefficient over concentration of H2 times concentration of F2. So that equals our concentration of HF, which is 2x quantity squared. You have to be very careful writing that 2x squared, because if you just think in your head 2x squared, you might write it like this. And you don't want to do that, okay, because then you won't square that 2, and that 2 has to be squared. It's part of that value, okay? So we don't want to do that. We want to put the quantity of 2x and square it. And then we have 1 minus x times 2 minus x. We'll move that to the next slide here. So we have that 2x squared over 1 minus x times 2 minus x is equal to 115. Now, if you do a little algebra there, you end up with kind of a nasty little quadratic equation right there. As I have on that slide, those aren't particularly fun to solve. You can solve this in one of 2 ways. You can use the quadratic equation and do it by hand, or a lot of you have calculators that have a solver function, and you are certainly welcome to use that solver function. It's a good idea to learn how to use that because it comes in very handy in the sciences and in engineering. So if you have a calculator with one of those functions on there, I recommend that you learn how to use it. If you don't know how to use it, feel free to stop on by my office. I know how to use the solvers on quite a few different calculators. If you have one, I can try to show you how to use it. So when we solve this, because we have a quadratic, we get 2 values of x. We have 2.14 and 0.968. If you have a quadratic, you will always have 2 solutions, and this is no exception. So as it turns out, only one of these values will make any sense, and that's the 0.968. The reason 0.968 is the only one that makes any sense is because if x were equal to 2.14, it means I would have lost more H2 and F2 than I started with. And you can't do that. You can't use more H2 than you have, right? So we have 0.968 is the only one that makes practical sense. And when you factor that value for x into your icebox to solve for your equilibrium concentrations, for the H2, you have 1 minus x. So we have 1 minus 0.968. That gives us 0.032 for the equilibrium concentration of H2. We have, for F2, we have 2 minus x. So we have 2 minus 0.968. So we have 1.032 at equilibrium. And then for our HF, it's 2 times x. So 2 times 0.968. And we get a value of 1.936. So that's kind of the basics of how to do ice boxes, equilibrium, constant calculations. There are certainly some other more complex concepts in there. You will see some in your book. I do welcome you to gaze through there, look at some of the tricks that can occur for certain types of reactions there. But like I said, that's the basics. If you have any questions on anything we covered in this particular portion of the lecture, please contact me.